Of course, the radiological characterization is actually the essential basis for the further execution of all work, like the clearance of radioactive waste, decontamination, and so on. In fact, the procedures still have a high degree of conservatism. This actually needs to be reduced to get to the necessary throughput that clearance procedures simply need to have these days to provide the necessary input for final disposal in the CONRAD repository. This is because they are not produced before the total decommissioning is not carried out. And on the other hand, of course, to keep the total decommissioning period within tolerable limits. There are different activities in individual wastes, which of course cover as wide a range as possible. Think, for example, of absorber rods in the core. Think of structure materials which are activated over a wide range of several orders of magnitude, or also of residual materials contaminated at different levels, from a wide range of different waste. Of course, you can pack them nicely separately, the low activity waste into plain containers, those with high activity into the complex ones with high shielding and so on, to follow all the characteristics and all the requirements to the waste packages. However, it is better to mix them appropriately, also to take advantage of self-shielding and so on, to reduce herewith the total number of containers, and thus to make the process as a whole more effective and to reduce costs for the containers.
For decommissioning, most of the time we have two challenges, I would say. Those two challenges, how to have a very good efficiency at the same time, minimizing the amount of secondary waste, and trying to find some kind of waste that is very easy to be treated. And most of the time is solid waste. Solid waste are much more easier to be treated, to be collected than liquid waste or other type of waste. We have less volume of final waste than the initial product that we use at the beginning. As I said, we have a decontamination factor between 17 to 25, so on average 20, I would say. So we decrease by 20 times the initial dose rate. And lastly, it's very important for this one is the final waste are actually 100% minerals. So there is no organic component inside of the final waste. You have the contamination and the dried gel. And this is very important because if you have 100% minerals, no organic, there is no risk to have hydrogen. So it's very safe to be stored in storage area for a very long time.
In Germany, we have the special case that we are decommissioning all the nuclear power plants more or less at the same time. That means we are doing industrial decommissioning. This is exactly what the system is designed for, because there is the challenge that we have to create a throughput here, and this with the know-how that the system must be included somehow in terms of radiation protection. A clearance is usually achieved by a decision measurement, and this is done by a direct measurement, a gamma spectroscopy through the germanium detector or through the large clearance monitor. And the large clearance monitor is the one that regulates most of the mass flow. This is where we want to reach a quantum leap for the release for the decommissioning of nuclear facilities. We then looked around where to find a model that may already has this type of hotspot detection in some form, and we found it in medical physics, because here radiological imaging technologies are used. We have adopted exactly this model of evaluation and have adapted it, however, to the nuclear conditions, that is the DIN ISO 11929. And of course, we have the advantage that we don't have to inject anything, because at worst we already have activity in the waste. With this technique, we can now identify hotspots to a certainty of 95%, which is essentially now just a computationally intense task.